Assalamu alaikum. Today we are going to start our lecture series on variable load requirements of power system. Let us move on. First of all, we have to understand that the demand on power station or load on power stations it varies constantly based on consumer activities. So, based on what particular set of consumers are doing at a particular time, their demand may vary, and that ultimately affects the overall demand on the power station. So, the overall demand on power station continuously fluctuates. So the electrical generators, this is also a fact that electrical generators will give maximum efficiency when they are loaded around 80% of their rated capacity. So if the generators which are working in a power station are loaded to 80% of their rated capacity, around 80% of their rated capacity, then they give their maximum efficiency. It doesn't mean that we cannot load them beyond 80% of their rated capacity, but normally we like to plan the working of or operation time of different generators such that all of the generators work around 80% of their rated capacity, and hence we can achieve maximum efficiency operation from those generators. So varying load on the power system makes this objective difficult to achieve. Obviously, your load is constantly varying, and you'll have to constantly vary the output from these generators. And on the other hand, you also want to operate them near 80% of the rated capacity. So this objective of operating generators at their maximum efficiency point becomes somewhat complicated when varying load is involved. So what are the complications that may arise from variable load on power station? So number one, you need additional equipment to adjust the supply of power with demand. Obviously, you need to adjust your power supply with demand, and you will need additional equipment for that. A good example of this is a steam power station, a coal-fired steam power station. In a coal-fired steam power station, which we have discussed previously, you see there are certain governors and control valves which are used to control the amount of steam being produced by the boiler and the amount of steam which enters the steam turbine. And these devices are needed because of the variable load requirements of the power station. uh, in an ideal case, in an ideal world, if the load on power system would remain constant for a given time, then the complexity of these devices and the number of these devices would be much reduced, and the plants would be much simpler. But that is not the case, so these devices need to be added in the power station. Number two, the variable demand necessitates the use of many alternators. So you need more than one alternator to in a power station. You cannot simply install one alternator in a power station, because in times of low load conditions, this alternator will work at a very reduced capacity, and on that capacity its efficiency might be very low. If efficiency of the system generating power is low, then obviously the cost of electricity being produced would increase. So the minimum cost which you will achieve from your power station will be when the generators are working at their maximum efficiency, or systems are working at their maximum efficiencies. Then you will be able to get the most out of the system for a given input, and consequently the cost of electricity would be lowest for that. Let us now talk about load curves. So a load curve shows the variation of load on power station with respect to time. So time is drawn on x-axis and load is shown on y-axis, and the curve which shows the varying load with time on this graph is known as load curve. So we might have different types of load curves depending upon the timeline which you have considered. So we may have daily load curve, which will record load variations in a day. So your time axis will have the number of hours in a day, and on top of each of those hours, on top of each half hour, the value of average load which occurred during that time slot would be placed. So this is a sort of sample and hold principle. So you take the average of the loads which occur during a half hour time slot, and that average is represented as the overall average load of the uh, designated time slot. So if the time slot is half hourly time slot, then you'll have average of load occurring on that on the power station for that half an hour, and then you will represent these half hourly average loads on the load curve. So the schedule for the size and number of generators to be operated in the power station are drawn basically based on the daily load curves. So daily load curves are seen, and the operational schedule for different types of power plants is devised. For example, from it may be that from 10 a.m. to 2 p.m. Steam power station will be working in with hydroelectric power station, and from 2 p.m. onward to 6 p.m. Steam power plant may be working, but hydroelectric power station may not be working. So the schedule like that is derived from daily load curves. Based on the load which the power system has to serve, we decide which power stations would be operational, and how many generators in the respective power stations will be operational, and what will be the size of those generators. Then we move on to monthly load curves. Obviously, as the name implies here, that this load curve will give load variations on a monthly basis, and at specific times in a day, the that average load is taken for that particular time, and then these load curves are drawn. For example, they are generally used to fix the electricity rates. For example, if the load at midnight, like at 12 a.m., that may vary on daily basis. So the average of load at midnight is calculated and shown as midnight monthly load curve. So like this monthly load curve can take on many forms. So one form may be that all the 30 or 31 days of the month are shown on the x-axis, and on the y-axis the average load against each day is plotted. Or in another scenario, the time axis may only contain 24 hours, but those 24 hours, for each hour we have the average of 31 days, and the time the load which occurred on the on that particular time across the 31 days. Like let's say on top of 6 p.m. on written on the x-axis, the load which is shown on top of that may be the average of loads which occurred at 6 p.m. throughout that month. So that is the second form of monthly load curve. So annual or yearly load curve shows the load variations over months of the year. So normally this annual load curve is used to determine the annual load factor, and I have included some exercises as well to give you a taste of how this is done. So in this slide we can see the daily load curve, and this daily load curve is showing you the load variations which have occurred in the day. So for example, from this load curve you can see that the highest peak is at 6 p.m. around 6 p.m. You can say between 6 p.m. and 7 p.m. there is a highest peak which is of 6 megawatt. So this highest peak is, as you recall, this is called the maximum demand and during this day. So the average load may be taken from this load curve, and you can do you can calculate the area under the curve and divide that area under the curve with the number of hours in a day to get the average load in megawatts. Or you can for that you need the curve, the equation for this curve which is being shown here. That is a complicated curve. Another simplified method, which is just an approximation, is to sample and hold. Like uh, the average load which occurs at 12 midnight is taken to be the load which occurs throughout this 12 to 2 period. Or you can say that you can take 1 hourly sample and hold values. So the value which occurs at 12 midnight or 12 a.m. is sampled, and then it is held for this amount of time up to 1 a.m. and then the sampling is done again, and then the new value is held up to 2 a.m. and so on. You can form rectangular sections of this curve by a sample and hold, and then you can approximate the total kilowatt hour or megawatt hour energy consumption. After that, you can divide that megawatt hour energy consumption with the total number of samples which you took, and that will give you the average load in a day. So that is one way to do this, and that is an approximation, obviously. But if you take the samples, enough samples, that approximation can become very accurate. Let us now talk about demand factor. So demand factor, before we move on to demand factor, we need to find out figure out different terms. So first of all, we need to talk about continuous ratings, which are specified on the different devices. So continuous rating, for example, for a 100-watt bulb, which you purchase from the market, the continuous rating for that 100-watt bulb is 100 watts. Like that bulb, if you switch that bulb on, it will consume 100 watts and generate light, and it will keep on consuming 100 watts constantly at all the times until that bulb is switched off. So that is the continuous rating of that bulb. The continuous rating for a refrigerator might vary based on its duty cycle, the time for which it is on and the time for which it is off. So the continuous ratings of all the equipment are which are connected to the supply. The sum of continuous ratings of all the equipments connected to the supply for any given consumer is known as the continuous is called the connected load of that consumer. So obviously this term is not that important to us, because a user might have a consumer might have a lot of connected loads, but he might not switch them all on at the same time, and he will not switch them all on at the same time. So a connected load is one of the terminologies. Next, we move on to maximum demand, which we have already discussed in the previous slides. So maximum demand obviously is the greatest load which comes on a system at any given time period. So I'm not going to go into details about that because we already understand this terminology. So obviously this maximum demand will be less than the connected load. Obviously the number of devices you switch on will be lower than the number of devices connected in a premises. So this maximum demand will always be lower than connected load. And demand factor is calculated before we move on to demand factor. There is another thing about maximum demand, that your power stations must be able to meet these maximum demands. They are not required to meet the connected loads, but they are required to meet the maximum demand. Demand factors are calculated based on this formula, which is the demand factor is basically the ratio of maximum demand to connected load. Now let us talk about load factor. So average of loads occurring on power station in any given period, say be it day, month or year, that is called average load or average demand. So this is obvious, so I'm not going to go into details about it. So average load can also be found or calculated from this formula. So you take the number of units generated in any given time period. By units we mean the energy in kilowatt hours. So you take the number of units generated in any given time period, divide them by the number of hours in that given time period, and you'll get the average load consumption during that time period. Load factor or LF is defined as the ratio of average load to maximum demand. So this is a very important factor, as average load. It gives information about average load and maximum demand, two most important things for a power station. So load factor is average load divided by maximum demand. Obviously, a high load factor implies that the average load on the system and the maximum demand, if the maximum demand on the system and the average load on the system uh, are exactly equal, say they are exactly equal, then that means that you only need to install a plant with maximum demand. The plant has to meet the maximum demand, and that will also be able to meet the average load. in practical scenarios in real life, average load is always less than maximum demand, and it is very less than maximum demand. Say 40%, it is normally 40% of the maximum demand. But if the average load is somewhat 60% of the maximum demand, then that plant is able to generate cheaper electricity as compared to the plant which is working with a load factor of 40, or where the average load is 40% of the maximum demand. And that is obvious because the second plant is able to serve more load with a lower capacity as compared to the first plant. I'll go into details about it, and I'll explain what I am talking about here in the question and answer sessions, QA sessions, which we'll conduct about this. So average load, you can calculate average load from load factor as a product of maximum demand and load factor. And if you want to find out the kilowatt hours per annum, or units generated per annum, or units consumed per annum, you can simply multiply average load with the number of hours for which the plant was operation in a year. So if the number of hours are not mentioned for any given example, then you take 8760 hours, which are the number of hours in a year. Otherwise, you use the number of operational hours of a plant if you want to know how much kilowatt hours were actually generated by the plant. So in this formula which is written here, maximum demand in kilowatt multiplied by load factor is in fact equal to average load. So you can also write average load multiplied by number of operations.